Hey everyone, Mr. Newman here, and today we're going to learn about parent functions. What we're going to do is we're going to first graph these parent functions. Parent functions are like the basic functions that we'll start with in this unit. And we're going to create a table of values for those in order to graph them. So, first off, the absolute value function. The absolute value technically means the distance from 0 on the number line. But what that does is it simply makes negative numbers positive or negative value positive, and it keeps positive values positive. So the absolute value of 10 is 10, but the absolute value of negative 10 is positive 10. So right here, if I have negative 3 as the input, the absolute value of negative 3 is 3. The absolute value of negative 2 is positive 2, and the absolute value of negative 1 is positive 1. The absolute value of 0 is just 0, because it's neither positive nor negative. And now on the positive side, the absolute value of 1 is just 1, absolute value of 2 is 2, and the absolute value of 3 is 3. So you can see all the negative numbers just become their positive counterparts, and positive numbers stay the same. When you graph the absolute value function, and this is what you'll do in future graphs here on this paper, let's just plot those points, and then we're going to outline what we see. Notice they make two straight lines that come together in a V shape. That's the absolute value function. For the square root function, you know that you cannot take the square root of a negative number. So if the input is, for example, negative 1, we have to say D and E does not exist. In fact, none of the negative numbers can be plugged in. So the first number we can plug in is actually 0, and the square root of 0 is 0. The square root of 1 is 1. Square root of 4 is 2. And the square root of 9 is 3. When we plot these points, we get a shape that looks like this. And when we connect the dots, it looks like this. Make sure there's an arrow on the right side, but there's no arrow on the left side because the function stops at 0. Also, if we were to turn this graph on its side, it would look kind of like half a parabola function. And there's an important reason for that you'll learn about another day, is that the square root function and the parabola, the quadratic function, are inverses of each other. For the step function, there are two specific kind of step functions we're going to talk about: the floor and the ceiling step functions. The floor step function always rounds down the number. The ceiling step function always rounds it up. So what do I mean by that? Well, if you start with 0, round that down, you keep 0. So any integer, that's like a whole number, you just keep that number in the step function. But if you have a decimal, like 0.4, you're going to round that down to 0. Even for decimals that are bigger than half, so like 0.6 for example, when we're dealing with the floor function, we round that down. So the nearest integer below that is 0, so we're going to round it down to 0. Number 1, though, is a whole nother number, as an integer, so 1 stays itself. You round it down, but it stays the same. 1.4, we round that down, and that rounds down to 1. 1.6, we round that down, and that rounds down to 1 as well. And the number 2, well, it will stay itself because it's another integer. So you notice what we get, any inputs that are decimals, we just round it down to the next lower whole number, or integer. So if I plot those points, 0, 0, and 0.4, 0, and 0.6, 0, they're all on the x-axis, where y equals 0. And if I want to plot all the points like that, well, I'm going to make that a straight line, going from 0 all the way up to 1. Now notice 0, 0 is filled in, because 0, 0 is on the line there. 1, 0 is not filled in, because 1, when you plug in 1, you get out a value of 1. That's up there at 1, 1. Now if we plug in 1.4 and 1.6, we get the same thing. Those are also on the horizontal line where y equals 1. And if we connect all those dots, we can again get this pattern where the first hole is filled in, the first dot is filled in, rather, the first point, because 1, 1 is in the function. But 2, 1 is not in the function because 2, when you plug in 2, you get 2 up there. And you notice this pattern will repeat over and over, where you have a solid line and then a hole, solid line, then hole. And this even works on the negative side as well. In other words, if I plugged in, say, negative 1.5 right here, the output would be negative 2, because that is the floor, the rounding down of negative 1.5. And you notice why it looks like why it's called a step function is because it looks like stair steps. What's weird is this function is not continuous. There are breaks in it. For the next function, cubic function, that means multiplying the number by itself 3 times. Negative 3 cubed, for example, is negative 3 times negative 3 times negative 3, which is negative 27, because there's an odd number of negatives. So any input that is negative will remain negative. Negative 2 cubed is negative 8, negative 1 cubed is negative 1, 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, and 3 cubed is 27. Notice how big this function gets very quickly. Even at 3, we're already way off the graph. Technically even at 2, but we'll try to plot those points here. So I plot those 5 points. I can't plot 3, 27. I can barely plot 2, 8, and negative 2, negative 8. So we're going to connect these dots, and notice in the middle how it's curved. We call that a saddle point because it looks kind of like a saddle. Cube root function. This is what multiplied by itself 3 times gives you that number. So this is the opposite of the cubic function in many ways. The inputs and outputs are actually just switched. The cube root of negative 27 is negative 3 because negative 3 times negative 3 times negative 3 is negative 27. And when we work backwards, we get these numbers. When we plot these, we'll get something that looks like this. And notice this looks very similar to the cubic function. It's just flipped on its side. And again, there's a good reason for that. That's because the cubic function and the cube root function are inverses of each other. All right, for the piecewise function, what you want to do is you want to consider the 2 parts of this function. So for example, if I'm plugging in negative 3, I'm going to look here and go, all right, where does negative 3 apply? Is it going to be this top function here? Or is it going to be with the bottom function? And the way you tell that is you look over here to the right. It says if x is less than 1, then you use this up here on the top. However, if x is greater than or equal to 1, you use this bottom function. Apply that. And that's exactly what piecewise functions are. They're 2 different functions that are mashed together, and part of the time you use one of the functions, part of the time you use the other function. So where does negative 3 apply? Well, negative 3 is less than 1, so we're going to apply the top function, negative x squared plus 4. When I say apply, let's plug negative 3 into that. Now notice a few things. I plugged negative 3 into parentheses, and negative 3 goes on the inside, but the negative from the function out here still needs to go on the outside right there. So we apply that. We need to remember our order of operations. Negative 3 squared is positive 9. So that's why I put a positive 9 inside the parentheses. However, that term is still negative because we have the negative out in front, which I did not square yet. I had to square the insides alone because of the order of operations. Now that parentheses 9 with a negative in front of it is negative 9 plus 4, which is negative 5. So I got negative 5 because I applied the top function. And the reason I applied the top function was because my input, x, was less than 1. If the input were greater than 1 or equal to 1, we would have used 2x minus 1 instead, and we'll get to that in a moment here. All right, let's try another one, negative 2. Is negative 2 less than 1, or is negative 2 greater than or equal to 1? Negative 2 is less than 1. That means I'm going to use the top function. Let's plug it in here. Again, notice I very carefully wrote down the negative from the negative 2. And I wrote down the negative from the function. One of the many reasons I put parentheses is so I have both of those if we need both. However, negative 2 squared is positive 4, so I will plug that in there, and negative 4 plus 4 is 0, so that is my output for negative 2. Negative 1 is less than 1, so we'll apply the top function again. Again, following the order of operations, we get 3. And 0 is also less than 1, so we're going to apply the top function one more time here, and we get, well, 0 squared is 0, and negative 0 and positive 0 are the same thing, so we get 4. What I'm going to do here is I'm going to draw a little dotted line. The reason for that is because this next one is the first one that applies to the other function. You see, 1 is greater than or equal to 1, so we're going to use this function now, 2x minus 1, to apply to 1, 2, and 3, because all of those are greater than or equal to 1. So let's plug that in here. 1 being plugged in here, 2 times 1 minus 1 is 2 minus 1, which is 1. So I plug in 1, I get 1 out. Notice how 1 is kind of like the cutoff here. See how there's a 1 right there? X is less than 1, applies one function, and x is greater than or equal to 1, we apply the other function. So what I'm going to do on my graph, to help me graph this, I'm actually going to draw a vertical dotted line at x equals 1. And on one side of this dotted line, one of the functions will be graphed. On the other side, the other function will be graphed. The dotted line just helps me figure that out. So let's apply 2 now. Now that I apply 2, we're going to use the bottom again because x2 is greater than or equal to 1. When we plug it in, we get 3. So 2 comma 3 is a point. And the last one, I'll just write down right here. Plug in 3 because it's greater than or equal to 1. 2 times 3 minus 1 is 5. So let's plot these points. Negative 3, negative 5, negative 2, 0, negative 1, 3, and 0, comma 4. That makes one function over here. The other one, 1, 2, comma 3, and 3, comma 5, makes the other function. Notice the arrows I drew only go away from the center here because we have only part of each of those functions. It's a piecewise function because they are pieced together. Now, one other little thing I'm going to do, and I'll share more with you about this in the future and in class, is I'm going to actually need to complete this gap. You see how there's a gap right in here where nothing is? Because it's to the left of that dotted line, I'm going to actually apply the top function because we're still less than 1 when we're in that gap, so the top function applies. And when you plot points there, you get something that looks like this. Notice I made an open circle on the point 1, comma 3. That's because if you were to plug in 1 into the top function, you would get 3, even though we're technically not allowed to, which is why it's an open circle. Well, thank you very much for watching.